This is Chapter 11, Section 2. We're going to be looking at several gas laws in Section 2 and Section 3. So let's get started with our first three basic gas laws. And the first one is going to be Boyle's Law. I know in the PowerPoint it goes through a very long process of pointing out what each of them are, but I'm going to do a condensed version for the first three laws, and then we'll quickly go through what's in the PowerPoint. So the first gas law is Boyle's gas law. And Boyle's gas law deals with two different variables. They are pressure and volume. We are going to leave mass and temperature constant. And with this one, pressure and volume, as pressure increases, volume decreases. So that is an inverse relationship. If we were to put this into equation form, it would be P times V equals K, where K is a constant. So if you multiply the two variables, pressure and volume, you will get a constant value. It depends on what the gas is. But since these are inversely related, you could even flip the arrows as volume increases, pressure decreases. Writing this out, P1 V1 equals P2 V2. A lot of our math problems are going to be set up with an initial and final condition. So initial or starting condition is going to be our 1s, and then final or ending condition will be the subscript 2s. And if you were to plot out data with pressure and volume, then your graph would be shaped like a hyperbola. You would not touch the x-axis or y-axis. That'll get really close to each of those, but pressure and volume would be on those two axes. So that is Boyle's law. The next law is Charles's law. And Charles's law deals with two different variables, but they are temperature and volume. We are going to leave pressure and mass constant. And this one, as temperature increases, so does volume. So for these, you would say that they are directly related. They either increase together or decrease together. If we were writing this out, volume divided by temperature equals a constant. And again, I like to point out when we talk about inverse and direct relationships, direct starts with the letter D, and divide starts with the letter D. So if you divide the two variables to get a constant value, they are directly related. And if we were to set this into an initial and final scenario, because temperature is in the denominator, if you want it back in the numerator, you have to flip which side of the equation it is on. So notice that the temperatures, the 1 and the 2, have been flipped around. Again, we have everything in what's considered the numerator position, nothing in the denominator. So those temperatures have to get flipped. And for this, since they're directly related, they would give you some sort of linear graph whenever you graph them. And the third gas law that we're going to look at is Gay-Lussac's law. Gay-Lussac's law deals with the variables temperature and pressure. And for these two, they are also directly related. So as temperature increases, pressure increases, or they both decrease together. And this one is assuming mass and volume of your gas are held constant. So since they're directly related, we are dividing the two variables to get a constant again. And if we were to set up initial and final conditions, again, if you wanted to get your temperature back into the numerator side of things, make sure you switch your temperatures around. And because these are directly related, you would still get a linear graph when you plotted the data. For all of our gases, we have to, when we work out problems, we have to be in Kelvin, the Kelvin temperature scale. I'm going to show you something on your reference sheet. So I took a picture of the pink reference sheet that you were given. Right now I'm talking about the Kelvin temperature scale, and to do a little bit of highlighting, right down here, that is the conversion from Celsius to Kelvin. So you add 273 degrees to your Celsius temperature to get it into Kelvin. Again, all the math we're going to do with gases, if temperature is involved, it has to be on the Kelvin scale. When we get to section 3, ideal gas law, right up here. So that's actually given on this sheet, PV equals nRT. We will get to it. And here momentarily in this section, the combined gas law. We will get to the combined gas law also. So just know that those are available to you as we work. Universal gas constant, that will come up in section 3. So you have 2 different versions of the universal gas constant with 2 different sets of units. We will get to both of those in section 3. And as I'm looking, it looks like that's pretty much it for our gases as far as information that you're going to have that you can work with. So again, Kelvin temperature. If you are given Celsius, you must add 273 to that Celsius number to get your temperature in Kelvin. If for some reason they ask for a final answer in Celsius, you must work out the entire problem in Kelvin and then convert back to Celsius by subtracting 273 to get your final answer in Celsius. Again, these problems have to be worked out in Kelvin. So I'm going to quickly go through some of these slides. Most of this, unless I stop and make a particular point about something, you have been given the foundation of what I want you to know. Some of the specifics I'm not really worried about. You can read through it yourself and then move on. I did show you that particular graph. It's volume versus pressure, and you can see it is shaped like a hyperbola. We've gone over that initial expression. We have rearranged it to look like that equation that you will need to know specifically for Boyle's law. So let's get to a sample problem, show you how to work some of these out. Sample of oxygen has a volume of 150 milliliters, so please write this down for yourself in your notes. When its pressure is 0.947 atmospheres. Notice those first 2 numbers go together. So you have to realize, too, what units go with what. It says a volume of, but it doesn't have to tell you milliliters is volume. You should know that milliliters is volume. So I will mark that as the first volume given, V1, and that ATM is atmospheres. You should recognize that as a pressure unit, even though it tells you it's pressure. That's P1. What will the volume of the gas be? So they're asking us to solve for V2 if the pressure is changed to 0.987 atmospheres. So I would set up that equation. P1 V1 equals P2 V2 and plug in all of my information. Please use your units too when you plug everything in. 0.947 atmospheres. Because you want to make sure in this case your units match up so that they'll cancel. V1, 150 milliliters. P2, 0.987 atmospheres. And we are solving for V2. Should be easy algebra. Multiply 0.947 and 150. You will divide by 0.987 to get your volume. And your final answer, 144 milliliters of oxygen gas. So again, make sure you can put this into your calculator properly. And there is your final answer there after it's been rearranged. So this gets into Charles's law. Again, I've given you the basics for it. There at the bottom, it talks about the Kelvin temperature scale, why we use it, because the Kelvin temperature scale has an absolute 0 to it, meaning you cannot have a negative value on the Kelvin temperature scale. And for our gases, we can't have negative volumes or negative pressures. That does not exist for what we are doing. So we work on the Kelvin temperature scale. It is a linear graph. And we have already shown the equation for it. So we will work out a problem. So please write down this problem. A sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. What volume will the gas occupy at 50 Celsius if the pressure remains constant? So again, we do have variables that remain constant during some of these. This one's going to work with volume and temperature, so pressure and mass are constant. Let's see here. First volume given, so that is V1. This temperature given is T1. And then it says at what volume, so we'll be solving for V2, and that is the second temperature given. Now, when we set this up, remember for Charles's law, the temperatures, I got to write down the right variable. We're dealing with volume. V1T2 equals V2T1. So we want to make sure we swap those temperatures around because we were pulling them out of the denominator. And also our temperatures need to be changed to Kelvin. So if I go up here and I do 25 degrees Celsius, add 273 to that to get to your Kelvin, that is going to be 298 Kelvin. And the other one is 50 degrees Celsius, add 273 to get to Kelvin, that is 323 Kelvin. So we'll have to plug in those numbers for T1 and T2. So let's get to plugging again. V1 is given as 752 milliliters. T2, again, this is common for people to get their temperatures not swapped around properly, but T2 is 323 Kelvin. V2 is what we are solving for, and T1 was 298 Kelvin. Again, if you're going to solve for V2, the 298 must be divided on the opposite side. That's how we get rid of it algebraically. And our final answer is 815 milliliters of neon. Please make sure you can get your correct answers. So there is the final within the PowerPoint, rearranged for you. And then it moves on and we're going to talk about Gay-Lussac's law, which we've already highlighted for you. It is a linear graph, but you can see some data there. We've already looked at the initial setup mathematically for Gay-Lussac's law. And here it is set up with a initial and final scenario, your 1s and your 2s. And let's go work out a sample problem. Please write it down. A gas in a container is at a pressure of 3 atmospheres, so that's our first pressure, and 25 degrees Celsius, first temperature. Again, temperatures must be converted to Kelvin. Directions on the container warn the user not to keep it in a place where the temperature exceeds 52 degrees Celsius. That's our second temperature. What would the pressure be at 52 Celsius? So we are solving for P2. Again, for Gay-Lussac's law, because they're directly related, temperatures would originally be in the denominator. So we swap them around to get them back into the numerator. And we'll go up here and do a couple of temperature conversions. Well, I'll just verbally say them. You're going to plug them in. P1, 3 atmospheres. T2, that 52 degrees Celsius, whenever you change it to Kelvin, you add 273. So you get 325 Kelvin. P2 is what we're solving for, and T1, the 25 degrees Celsius, add 273 to that, you get 298 Kelvin. And again, to solve for P2, algebraically, the 298 must go to the other side and be divided, and your final answer is 3.27 atmospheres. 3.27 atmospheres. So, there it is all worked out for you. Let's go look at a summary of our basic gas laws. So you got Boyle's, Charles, Gay-Lussac's. Avogadro's is thrown in there too. V equals K times N. For Avogadro's law, let's see, I feel like we're going to cover that soon. It will be covered in section 3. So the V is volume, K is a constant, N, you will find out what that represents. But now we're going to go and we're going to take Boyle's, Charles, and Gay-Lussac's law and combine them into what we call the combined gas law. So this is the 4th gas law that you're learning in this section. We're going to take the P, the V, and the T and combine it. And if I were to show you this video, this is what it's going to show you. Put our ones in here. So an initial and final condition with all 3 variables that we've worked with so far. And if we rearrange that and get our temperatures back into the numerator, then we have P1 V1 T2 equals P2 V2 T1. That right there is the main combined gas law equation that I would want you definitely to be familiar with. The combined gas law equation is on that pink sheet in the first form. I prefer the second form that I have circled just because everything's in the numerator. Again, temperature has to be in Kelvin. But you could have used the combined gas law equation for all the equation itself to solve for any of the first 3, Boyle's, Charles, or Gay-Lussac's law problems. You would have marked through the variable that was held constant. So if you were working with Charles' law and pressure was held constant, just mark through P1 and P2. Just like this. Mark through them. You won't even use it since it's constant, and notice you still have the proper equation left over. But you do need to be familiar with which gas law goes with which set of variables. So let's go work out another problem. Please write it down. And it says that a helium-filled balloon has a volume of 50 liters, so V1 at 25 degrees Celsius, and 1.08 atmospheres. So we have V1, T1, P1. What volume, so we're solving for V2, will it have at 0.855 atmospheres? That's the second pressure, and 10 degrees Celsius, that's the second temperature. Again, temperatures have to be converted to Kelvin. Notice we're working with all 3 variables, so absolutely set up the combined gas law equation. Swap those temperatures around. And we'll get to plugging these in. So P1 is given, and again, make sure your units match up. Liters, we'll be solving for liters. We'll get all of our temperatures in Kelvin. I see atmospheres and atmospheres. So 1.08 atmospheres for pressure 1. Volume 1 is 50 liters. Temperature 2 is 10 degrees Celsius. So add that to 273. You get 283 Kelvin. P2 is 0.855 atmospheres. V2 is what we're solving for. And T1, 25 degrees Celsius. That in Kelvin is 298 Kelvin. And now we solve. Again, mathematically, you want to bring over, if I were to show you the division, to get V2 all by itself, you've got to divide by the 0.855, divide by the 298 to get V2 all by itself. So you would divide by both of those on each side. Notice atmospheres cancels. And the 298, notice that your K for Kelvin cancels. And you would still multiply 1.08, 50, 283. Divide by 0.855, divide by 298, and your final answer is 60 liters. So 60 liters is your final answer. Please make sure you can get that. So there is the final problem rearranged. Again, plug it all in. That is the end of section 2. You should know Boyle's, Charles, Gay-Lussac's laws, the combined gas law that takes all 3 of those and puts them into one equation. And again, you can use the one equation to solve any of those gas laws within this section.